A magnetometer is an instrument designed to measure the strength and direction of magnetic fields. In the context of brain imaging, magnetometers must be incredibly sensitive because the magnetic fields generated by neural activity are extremely weak, typically in the range of pico to femtoteslas. To put this in perspective, Earth's magnetic field is around 50 microteslas, making brain signals billions of times weaker. These magnetic fields arise from the flow of electrical currents during neuron firing, which creates a measurable magnetic field that magnetometers can detect if they are sensitive enough. Superconducting quantum interference devices, SQUIDs, are the most commonly used magnetometers in brain imaging because they offer extraordinary sensitivity. SQUIDs operate at cryogenic temperatures, very close to absolute zero, using superconductors to detect minute changes in magnetic flux through quantum interference. These changes are translated into an electrical signal, which corresponds to the magnetic field generated by neural activity. Imagine being in a huge concert hall with thousands of people talking loudly, representing the Earth's magnetic field. Now, somewhere in the far corner, a person whispers, "This is the brain's neural activity." A normal microphone wouldn't pick up this whisper, but a precision magnetometer like a SQUID is like a super-sensitive directional microphone that can isolate and amplify that whisper, making it audible despite all the noise around it. Magnetoencephalography, or MEG, is a non-invasive imaging technique that records magnetic fields produced by electrical activity in the brain. When neurons fire, they generate electrical currents, and according to Maxwell's equations, the foundation of classical electromagnetism, these currents create tiny magnetic fields. Megarrays use multiple magnetometers to detect these fields in real time, offering millisecond-level temporal resolution. This is particularly useful for studying fast brain processes like sensory perception, motor control, and cognitive functions. In patients with epilepsy, MEG is used to pinpoint the exact location of abnormal neural activity that causes seizures. This localization allows for precise surgical interventions where the problematic brain tissue is removed without damaging surrounding healthy areas. MEG's ability to track brain activity in real time also aids in mapping the brain's functional networks, such as how different regions communicate during decision-making tasks. Think of MEG like a weather radar. In the same way radar systems track thunderstorms, MEG tracks neural storms in the brain, bursts of synchronized electrical activity that produce detectable magnetic fields. These fields can tell scientists where and when specific brain functions occur, much like a radar map shows the intensity and location of a storm. Advances in quantum sensors have revolutionized magnetometry, enabling the detection of even weaker magnetic fields than traditional sensors like SQUIDs. One of the most promising technologies is based on nitrogen-vacancy in NV centers in diamonds. NV centers are atomic scale defects in a diamond's lattice, where a nitrogen atom replaces a carbon atom next to an empty site, vacancy. These NV centers are extremely sensitive to magnetic fields because of their quantum spin properties, allowing them to detect magnetic fields at the nanoscale and at room temperature, unlike SQUIDs, which require cryogenic cooling. NV centers have been used to measure the activity of single neurons by detecting the magnetic fields generated by their action potentials. This opens the door to ultra-high resolution brain imaging, where scientists can study the behaviour of individual neurons or small groups of neurons, something previously impossible with conventional techniques. Imagine trying to read a book in a dimly lit room. Traditional magnetometers are like regular flashlights. They provide general illumination, but miss fine details. Quantum sensors, like NV centres, are akin to using a laser pointer to focus on and illuminate the tiniest letters, revealing minute details that were previously hidden in the darkness. Neurons communicate by transmitting action potentials, which are rapid electrical impulses that travel along their axons. When an action potential occurs, it triggers the flow of ions, charged particles, across the neuronal membrane, creating an electrical current. According to Ampere's law, any moving electrical charge generates a corresponding magnetic field. While the magnetic fields from individual neurons are incredibly weak, when large groups of neurons fire together, for example, during synchronized brain activity, their combined magnetic fields can be detected outside the skull. When a person moves their hand, neurons in the motor cortex fire synchronously, generating an electrical current and corresponding magnetic field. MEG can detect these magnetic fields, allowing scientists to observe how the brain controls voluntary movement. This information is valuable in treating patients with motor disorders like Parkinson's disease, where the coordination of movement is disrupted. Think of each neuron as a tiny, flickering light bulb. One light bulb alone doesn't produce enough light to be seen from far away. But when hundreds or thousands of light bulbs flicker together, their combined glow becomes visible. Similarly, the magnetic fields generated by many neurons firing together create a measurable signal that magnetometers can pick up. Magnetometry offers several unique advantages compared to other brain imaging techniques like functional MRI, fMRI, or positron emission tomography, PET. fMRI measures brain activity indirectly by tracking changes in blood flow, the bold signal, which lags behind neural activity by several seconds. In contrast, magnetometry, used in MEG, measures neural activity directly by detecting the magnetic fields generated by action potentials, providing real-time data with millisecond precision. Additionally, MEG does not require the use of contrast agents or radioactive tracers, making it non-invasive and safer for repeated use. In studies of language processing, MEG has been used to map the brain's response to spoken words in real time. By capturing neural activity with millisecond precision, researchers can observe how quickly different brain regions respond to auditory stimuli, helping to unravel the neural basis of language comprehension and production. Imagine trying to study a hummingbird's flight. fMRI is like taking a series of photographs, showing the bird at different points in time, but missing the rapid movements of its wings. Magnetometry, on the other hand, is like using a high-speed video camera, capturing the full motion of the hummingbird's wings in real time, showing every detail of its flight. Precision magnetometers have become essential tools in the diagnosis and treatment of neurological disorders. In epilepsy, MEG is used to identify the exact location of abnormal brain activity that leads to seizures. This allows surgeons to perform more precise interventions, reducing the risk of damaging healthy brain tissue. Magnetometers are also being investigated for their potential to detect early signs of neurodegenerative diseases like Alzheimer's and Parkinson's, where changes in brain activity patterns may precede clinical symptoms by years. In patients with Alzheimer's disease, magnetometers can help detect changes in the brain's default mode network, DMN, a network of brain regions that are active when the brain is at rest. By identifying early disruptions in this network, clinicians may be able to intervene before significant cognitive decline occurs, offering a window for early treatment. Imagine a mechanic diagnosing a car engine problem. Using a stethoscope, they listen for irregular sounds that might indicate trouble in the engine. Similarly, magnetometers listen to the brain's magnetic signals to detect irregular neural activity, allowing for early diagnosis and treatment of neurological disorders. One of the primary challenges in using magnetometers for brain imaging is dealing with magnetic noise. The human body produces its own magnetic signals from the heart, muscles, and even breathing, and the surrounding environment is filled with magnetic interference from electronic devices and the Earth's magnetic field. To isolate the brain's weak magnetic signals, MEG systems are often housed in magnetically shielded rooms, MSRs, which are lined with materials that block external magnetic fields. Even with this shielding, advanced signal processing techniques are required to filter out noise and enhance the brain's magnetic signals. A typical MEG room is made of several layers of mu metal, a highly magnetic material that absorbs and redirects external magnetic fields. By creating a near-magnetic vacuum, the brain's weak magnetic signals can be detected without interference from environmental noise. Without such shielding, external sources of magnetism would overwhelm the sensitive magnetometers, making brain signals undetectable. Think of trying to have a conversation in a crowded, noisy cafe. It's hard to hear the person you're talking to because of all the background noise. Magnetically shielded rooms are like stepping into a soundproof booth in that cafe. You can now hear every word clearly because the surrounding noise has been blocked out. Magnetometers are key tools in studying how the brain processes sensory information and performs cognitive tasks. For example, when a person touches a hot surface, the somatosensory cortex in the brain is activated, generating magnetic fields that can be detected using MEG. These real-time measurements allow researchers to understand how sensory inputs are mapped onto the brain, how different brain regions communicate during sensory processing, and how cognitive tasks like memory retrieval and decision-making are coordinated at the neural level. MEG has been used to study the brain's response to visual stimuli, such as flashing lights or moving objects. By tracking how quickly different areas of the brain respond to visual information, scientists can map the pathways that process these inputs and investigate conditions like dyslexia, where visual processing is impaired. Imagine the brain as a complex network of highways with sensory signals like cars travelling along different routes to reach their destination. Brain regions responsible for processing. Magnetometers are like traffic cameras, recording how quickly cars, signals, move along these highways and where potential traffic jams, processing delays occur. While magnetometers like those used in MEG offer excellent temporal resolution, tracking brain activity in milliseconds, they have relatively poor spatial resolution compared to techniques like fMRI. To overcome this limitation, researchers are exploring multimodal brain imaging, where magnetometry is combined with other imaging methods such as fMRI, optical imaging, or even electroencephalography, EEG. This approach allows scientists to obtain both high temporal and high spatial resolution, providing a more complete picture of brain function by showing both when and where neural activity occurs. In multimodal studies, MEG can provide real-time information on the brain's electrical activity, while fMRI can reveal the precise location of that activity. For example, in a study of visual processing, MEG might show when neurons in the occipital lobe, responsible for vision, fire, while fMRI could show the exact location of that activity within the lobe. Imagine trying to follow a concert, both by watching it live, seeing every movement, and listening to a recording of it, hearing every note. MEG is like watching the concert live, capturing every quick movement of the performers, while fMRI is like listening to a high-quality recording that shows where each instrument is positioned in the orchestra. Together, they provide a full sensory experience.
Brain imaging requires detecting extremely weak magnetic fields generated by neural activity. These fields are so weak that they are billions of times smaller than Earth's magnetic field. The challenge is to develop magnetometers that are sensitive enough to measure these faint signals while filtering out all the noise from the environment. What needs to be found? We need to understand how weak brain signals are compared to Earth's magnetic field. Determine how fast magnetometers, such as those used in magnetoencephalography, MAG, can capture brain activity. Explore how quantum sensors like Nitrogen-vacancy, NV, centers in diamonds can measure even fainter signals than traditional methods. Learn how neurons generate magnetic fields and why detecting them is so difficult. Understand the need for shielding to block environmental noise, allowing us to isolate brain signals. Step 1. How weak are brain magnetic fields compared to Earth's? The magnetic fields generated by the brain are extremely weak. So let's compare them to Earth's magnetic field. Magnetic field of the brain. B subbrain is approximately 10 to the power of negative 12 Tesla, which means picoteslas. Earth's magnetic field, B sub-Earth, is approximately 50 times 10 to the power of negative 6 Tesla, which means microteslas. Now, we take the ratio of these two fields. B sub-Earth divided by B subbrain equals 50 times 10 to the power of negative 6 divided by 10 to the power of negative 12, which gives 50 times 10 to the power of 6, or 50 million. This tells us that Earth's magnetic field is 50 million times stronger than the magnetic fields generated by the brain. This is why we need highly sensitive magnetometers to detect these faint signals. Magnetoencephalography, MEG, uses magnetometers to track brain activity in real time. But how fast is this real-time tracking? Let's assume we're studying brain signals that occur at a frequency of 100 Hz, meaning 100 cycles per second. To calculate the time between each cycle, T equals 1 divided by the frequency, which is 1 divided by 100. This equals 0.01 seconds, or 10 milliseconds. This means MEG can detect brain activity with a precision of 10 milliseconds, fast enough to capture rapid processes like sensory perception or motor control. Step 3. Quantum sensors, unlocking the smallest signals. Quantum sensors, like nitrogen-vacancy centers in diamonds, can detect even weaker magnetic fields than traditional methods like SQUIDs. Let's assume an NV center can detect a magnetic field of area. B sub NV is approximately 10 to the power of negative 15 Tesla, which is in femtoteslas. Meanwhile, brain magnetic fields are typically around 10 to the power of negative 12 Tesla. Now, compare the two. B subbrain divided by B sub NV equals 10 to the power of negative 12 divided by 10 to the power of negative 15, which gives 10 to the power of 3, or 1,000. This shows that NV centers can detect fields that are 1,000 times weaker than the brain's magnetic fields, allowing for ultra-precise measurements at the neuronal level. Step 4. How do neurons generate magnetic fields? Neurons generate electrical currents when they fire, and these currents create magnetic fields. This can be described by Ampere's law. The integral of B dot dl equals mu0 times I, where B is the magnetic field, I is the current, and mu0 equals 4p times 10 to the power of negative 7 Tesla meters per ampere. This is the permeability of free space. Now, assume a neuron generates a current of I equals 1 microampere. If we measure the magnetic field at a distance of R equals 1 millimeter, we can use the Biot-Savart law to calculate the field strength. B equals mu0 times I divided by 2per, which equals 4pi times 10 to the power of negative 7 times 1 times 10 to the power of negative 6 divided by 2pi times 1 times 10 to the power of negative 3. This gives us a magnetic field of B equals 2 times 10 to the power of negative 13 Tesla. This is similar to the brain's magnetic fields, showing that magnetometers need to be sensitive enough to detect fields around 10 to the power of negative 13 Tesla. Step 5. The need for shielding and noise reduction. Because the brain's magnetic fields are so weak, we also need to account for magnetic noise from the environment, such as signals from electronic devices, the heart, and even breathing. To isolate brain signals, MEG systems are housed in magnetically shielded rooms, MSRs. Let's assume the external magnetic noise is around. B subnoise equals 10 to the power of negative 6 Tesla. If the shielding reduces this noise by a factor of 10 to the power of 6, then the remaining noise is B subshielded equals 10 to the power of negative 6 divided by 10 to the power of 6, which equals 10 to the power of negative 12 Tesla. This brings the noise level down to the same order as the brain's magnetic signals, allowing the magnetometers to detect neural activity. Conclusion: what did we find? 1. The brain's magnetic fields are billions of times weaker than Earth's magnetic field. 2. MEG can track brain activity with millisecond precision, perfect for real-time monitoring. 3. Quantum sensors can detect even weaker signals, allowing for measurement at the neuronal level. 4. Neurons generate magnetic fields through electrical currents, but these fields are very weak, requiring extremely sensitive magnetometers. 5. Magnetically shielded rooms are crucial to block environmental noise, enabling accurate detection of brain signals. By calculating these values and understanding the physics behind neural magnetic fields, we see how precision magnetometers allow us to peer into the brain like never before.